Hey, welcome back. This is now 9.6, and these are my favorite tests for convergence of series. The ratio test, well, is my favorite. The root test is also in here. I don't really use the root test, but maybe you will. But anyways, here we go. So you got the ratio and the root test, and I kind of combine them all into one, unlike what the book kind of separates them out. But the deal will be you have a series with non-zero terms. So let A sub n be a series with non-zero terms. So all the terms are like 5, 6, and you don't have negative 10 or 0. So non-zero terms, and then you consider these these limits. Okay, so consider, we'll call it R. I think maybe they use rho in the book. Let me use rho. That's my Greek letter rho. So consider the limit of the absolute value of the consecutive terms of the series. So a sub n plus 1 over a sub n, kind of like what you do when you're doing your alternating series tests. Okay, this dude is called the ratio test. Or consider this other guy, this other limit, the nth root of the a sub n expression, and we want to include absolute values here. This guy is called the root test. But you know, the important one is for us is going to be this. Like maybe in some future universe you'll use the root test. I don't know. This one is more important. Okay, for our work. Okay, so you'll do those limits, and then you'll make a conclusion based off the limit value. So first, if the rho value is less than 1, then it's absolutely convergent. Or you could just say convergent, right? If the rho value is greater than 1, or if rho is equal to infinity, then it's divergent. And unfortunately, if rho equals 1, you got to try something else because the test is inconclusive. Okay, so let's get the root test out of the way and do maybe a ratio test, and then I'll try to walk you through the proof again. So here is the root, and the root test is good when you have a power of n, because when you take the nth root of it, that power of n will go away, and you could easily do the limit. Okay, so here we have our series. We know it's geometric and convergent, but let's just apply the root test for the sake of doing something which is relevant. So here I'm taking the limit of the nth root of 1 all over 3 to the n. Okay, and of course that will just be, if you rewrite it, you have 1/3 to the nth power raised to the 1 over n power, and then n times 1 over n is 1, so you just get the limit of 1/3, which is equal to 1/3. Okay, so our rho value is less than 1. That will imply via the proof, if we were going to, I'm not going to do the root theorem proof, but that would imply that it's convergent. Okay, so let's look at one more root test, and then we're going to leave it as is. So we have the series of n factorial to the nth power. So again, you see that n to that nth power is probably telling you try a root test to get rid of it, right? All right, so that's what we're going to do. Do the root test. So rho is the limit of n factorial to the nth power all over n to, and you can multiply those exponents downstairs, 7 to the n, and then we're going to raise that to that 1 over n. It's basically the same as taking the nth root. So taking the root of a quotient, you could take the root of the top and the root of the bottom separately. You'll get n factorial to the n times 1 over n, which is just n factorial to the 1, all over n to the 7, n times 1 over n, which is just n to the 7th. And in this case, the n factorial goes faster than exponential. So it's certainly going to go faster than that n to the 7th term, and it'll give us infinity, which will imply it's divergent. Okay, great. So the one we really like, though, is the ratio test. So let's take a look at it, and then I'll talk about the proof, and then we'll look at some maybe more complicated versions of the ratio test. So I have 5 to the n all over n factorial, right? So the limit of the absolute value of a sub n plus 1, which is 5 to the n plus 1 all over n plus 1 factorial, divided by a sub n, which is 5 to the n all over n factorial. And of course, the limits are always going to infinity. Okay, so this will be the limit of 5 to the n plus 1 all over n plus 1 factorial times n factorial all over 5 to the n. And then we simplify, right? So if you need to, you're going to write out everything in all of its glory. 5 to the n plus 1 is the same as 5 to the n times 5 to the 1. And I'm going to kind of collect that with the other 5 to the n part in the denominator. And then n factorial is really n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And then that's all over n plus 1 times n plus 1 minus 1, which is n times n minus 1, all the way down to 3 times 2 times 1. And then you could do your cancellations. Okay, so n factorial, and then there's another n factorial there. The 5 to the n's cancel. And it looks like you're left with the limit of 5 all over n plus 1, which is L over infinity, so that will just equal 0. That's definitely less than 1, so that implies it's absolutely convergent, which is convergence. Okay, so why the heck does this work? It's basically, you could do a direct comparison with the geometric series if the limit of the ratio of consecutive terms is less than 1. So we'll just do the proof of that part. Proof, suppose that the limit of the absolute value of a sub n, so we're given, maybe I should say, I'm given the series a sub n where a sub n are non-zero terms. Okay. So we'll suppose that the limit of a sub n plus 1 all over a sub n is equal to some number rho, which is less than 1. Okay. Then from that strict definition of a limit, we have this weird sequence again of these absolute values of consecutive terms, but the fact that this limit exists and is less than 1, so 1's here, and then maybe the limit is right here, we know that we can go out far enough such that any value that we pick, we can make it within some weird epsilon distance. In particular, we can make that distance so that it's less than 1 and above 0 as well. Okay? So as long as we go out beyond n, our terms of our sequence are going to be forced to be within that strip. Okay, so I'll say that in mathy speak. So due to the strict definition of a limit, we can find n a big N value such that for all n bigger than or equal to big N, we can form this inequality or as such. We could say little r is less than some r value. So if we let this L plus epsilon equal this big R in the picture to the right, I could say little r is definitely less than big R. And I apologize, we're using rho for our limit. So the L value in this case is the rho value, but in the book they call it little r, so I'm accidentally calling it little r as well, but it's really the rho value, so let me just put rho. We could put this r value above rho such that the big R value is less than 1, and then also we could say that this thing has to be bounded away from 0. I mean, we'll just say it's greater than or equal to 0, I guess, but I think ultimately we can say the rho value is greater than 0. Is that true? It doesn't seem, maybe it's not true, but okay. But anyways, the strict definition of limit will give us this inequality. And furthermore, we could say that a sub n plus 1, all of this absolute value of a sub n plus 1 over a sub n will be less than big R for in that interval for n greater than the big N. Okay. Okie dokie. So what? Well, multiply both sides by absolute value of a sub n. And these, I should really put like big N here to indicate that we are out beyond that big N. So I'll put big N plus 1, and then a sub big N in the denominator as well. Okay, so if we multiply then both sides, we get this inequality. A sub big N plus 1 is less than big R times the absolute value of a sub big N. Okay. And also then for the next term in line, a sub big N plus 2 all over a sub big N plus 1, this thing will be less than R as well, right? So if you were to multiply this first inequality by R, just hang on, I'll have R times the absolute value of a sub n plus 1 less than R squared times the absolute value of a sub big N. And from the second inequality, multiply both sides by a sub big N plus 1. So from there, you'll get a sub big N plus 2 is less than big R times the absolute value of a sub n plus 1. Combining those two inequalities together, you'll get this sort of chain. A sub big N plus 2 then is less than R times the absolute value of a sub big N plus 1, which is less than R squared times the absolute value of a sub big N, right? And then you could just continue this process ad infinitum, and then your series is going to be bounded above by this geometric series. Okay, so hence the series of the absolute value of a sub big N plus, let's say, some little n going from n equals 1 to infinity, this series will be kind of below. I don't want to say it. Maybe I should say the terms of the series will all be bounded above. So if you don't mind, I'm going to get rid of that and say that this thing will be less than, or well, we could just say strictly less than R, big R to the little n times the absolute value of a sub big N. Okay. So you could see it's true for n plus 1. You have this case, and what I'm saying is that's true in general from these inequalities. This whole picture of inequalities will show that tends to be true in general, right? So you get this statement next, and then a sub n plus 3 will be less than R cubed times the absolute value of a sub n, and we know that big R is less than 1, and the absolute value of a sub big N is just some constant. So we have the direct comparison. With this series, big R to the N times the absolute value of a sub N from N equals 1 to infinity, which is geometric, where our little r is equal to big R. Our a value is the absolute value of a sub N, but that's neither here nor there, and therefore it's convergent. Well, yeah, it's convergent, and then by direct comparison, this other series is convergent. Thus, the series of a sub big N plus little n from N equals 1 to infinity is also convergent. And of course, that thing is just our shortened variation of the this guy, the absolute value of a sub N. It's the same thing, it's just it has fewer terms, but that doesn't make a difference. So I talked about that previously. If you just chop off a couple of terms, it won't affect the overall behavior. And so this series converges. And then because the series of the absolute value of the terms converges, the original series is absolutely convergent. Okay, so there it is. It's a bit hard to follow, especially this chaining, forming these chains of inequalities. But you could always, it's always this process where you could start by just multiplying both sides of this inequality to get to here. And then because this inequality will hold for all n greater than big N, you can make another inequality by just incrementing the term by 1. So you just add a 1 to the subscripts, get this inequality, and then get this multiply both sides to get this inequality, and then hook that inequality up with this inequality, which is really this inequality right here, after I multiply by R. And then you're just repeating that process. So I guess you got to prove this process works. But hopefully it's kind of intuitive that it does. And then you could use the direct comparison test to complete the picture. But anyways, there it is in all of its glory. Again, it's not all that intuitive, right? You have the statement of the test. You have these criteria. It seemed very simple. But at the end of the day, the reasoning why it is the way it is because of this kind of complicated proof. Okay. Anyways, let's take a look at some other examples now of the ratio test. Let's look at problem 4. And I think in general these problems are pretty easy to handle. You just got to remember all the little criteria stuff that goes into it. So again, we're doing a ratio test. So I need a sub n plus 1. You just replace all the n's with n plus 1. Take reciprocals. You don't really need the absolute value here. Later on, the absolute values will become very important. We'll need to have them. But for now, it's almost like you can almost throw them in the trash for the most part, unless you have like an alternating series or something. 3 to the n plus 1 over 3 to the n. You could subtract exponents if you want. That's just going to be 3. And then you have n to the 5th all over n plus 1 to the 5th. And then do a circling job. So it's going to be 3n to the 5th over n to the 5th. And of course that will equal 3, which is greater than 1, which implies from our criteria above that the limit is divergent. Or sorry, the series is divergent. Okay. Let's look at some factorial problems. So one thing again to note that 2n factorial is not the same as 2n in parentheses factorial, right? 2n factorial is equal to 2 times n factorial. So n times n minus 1 times n minus 2, dot, 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 3 times 2 times 1. 2n in parentheses factorial is 2n times 2n minus 1 times 2n minus 2, blah, 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 3 times 2 times 1. Okay, those are different things. Additionally, if you have 2n factorial, to get a sub, so if this is your a sub n plus 1, so what is 2n factorial? That's 2n times 2n minus 1, 2n minus 2, blah, 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 3 times 2 times 1. This other one is going to be 2 times n plus 1 factorial, which is 2n plus 2 factorial. Okay. Maybe that's the point I'm trying to make here. So 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n minus 1, blah, 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 3 times 2 times 1. Okay, so hopefully that is clear. Let's look at number 6. So you have the series 2n factorial all over n to the 9th from n equals 1 to infinity. Okay, great. So I'm going to do my ratio test, my row value, then as limit of the absolute value of a sub n plus 1. So I need to replace n with n plus 1. So I got 2 times n plus 1 factorial all over n plus 1 to the 9th. And then that will be divided by, let's just multiply by the reciprocal, n to the 9th over 2n factorial. Okay, so we should be able to kind of expand those using what I just did above, and then simplify. Okay, so let's make this the video quiz. Okay, so this is a video quiz question, and you figured that out, and maybe I'll help you a little bit, but let me write it down as the video quiz before. Okay, so you'll have to show your work. So expand that 2n plus 1 factorial. Expand the 2n factorial, make the cancellation, and it should turn out that this will equal infinity. But please show work. Okay, it's divergent. Okay, let's look at number 8, which is always weird for people when they first see it. Something I found that would really help is if you took a discrete math class, kind of you'll deal a lot with, at least I dealt a lot with factorials in that class. They use a lot of factorials in computer science, which is what discrete math is kind of about. So, but you get proofs and stuff in discrete math as well, which would help. But anyways, here we are with this nasty looking critter. So how, this is my an expression. How do I get a sub n plus 1 for my row? Okay, so limit the absolute value. First off, the absolute value is gonna get rid of that -1 to the n. So you could just kind of kick that out of the pool. And then what is a sub n plus 1? So all you're going to do is kind of tack on an extra term. So you go all the way up to 5n, but then you tack on another term by replacing n with n plus 1. Like that. And the same for down below. So I keep the 6n plus minus 1, and then I'm tacking on 6 times n plus 1 minus 1. And then, of course, divided by, let's just multiply by the reciprocal of a sub n, which you just copy down. So overall, it's not that hard. You just have to keep your wits about you. all of this will cancel with this, all of this will cancel with this, and you'll end up with the limit of 5n plus 5 all over this thing. I kind of accidentally canceled into it. Let me get rid of that. It's actually just this part that cancels. 6n plus 6 minus 1 is 6n plus 5. And then you could do the circling. So you get the limit of 5, 6, which is 5, 6, which is less than 1, which implies absolute convergence. Okay. And one more. It's got n factorial all over n to the n from n equals 1 to infinity. Showing up the row value is the limit of the absolute value. You don't really need the absolute value. A sub n plus 1. So I replace n's with n plus 1's. And then multiply by the reciprocal. Okay. And then I'm going to, you can expand the n plus 1 factorial. You can put the n factorial on the left here if you want. And then you have n to the n. I think it helps if you rewrite n plus 1 to the n plus 1 as n plus 1 to the n times n plus 1, because you're going to see a nice cancellation, right? So the n factorial portion is all that. That'll cancel. But then you get this extra factor of n plus 1 that cancels with this guy way over here. And what you're left with is just the limit of n to the n all over n plus 1 to the n. And believe it or not, that is a 1 to the infinity type. So you convert it to an exponential. And at that point, it becomes infinity times 0. So you turn it into a fraction. And of course, we want to move the limit into the exponent. And then we could do L'Hopital's in the exponent. To do so it's the derivative of the natural log of n over n plus 1 is 1 all over n plus 1. But let's just take the reciprocal. So it would be n plus 1 over n, and then times the derivative of n over n plus 1. So that's low d high minus high d low all over the low squared. And then that will be all over the derivative 1 over n, which will end up being negative 1 over n squared. So these n's will cancel. You'll have a factor of n plus 1 will cancel with a factor of n plus 1 down here. And you'll have 1 all over n times n plus 1 times negative n squared over 1. Simplifying a little bit, you'll get e to the negative n all over n plus 1, the limit of that. And then, of course, the limit of that is negative 1. So you get e to the negative 1, which is 1 over e, which is less than 1, which implies it's absolutely convergent. Okay. Sorry if I blew through that one a little bit. Okay, as usual, thank you for watching, and I'll see you next time.